Okay. Well, thank you for joining us, everybody. My name is David Hansen. I'm one of the lead developers on Gadgetron, and I am here today to give you a tour of Gadgetron. Now, this is a tour much in the same way as a tourist bus going through London is a tour of London. Like we will give you we'll cover everything, but nothing in great detail today. It's more to give you like an overview of what's in Gadgetron and to introduce you to some of the key concepts that will be used throughout the online class. So let's start with sort of the obvious question: what is Gadgetron? Now, in Zoom, if you press the participants button, there should be a button to raise your hand. If you have used Gadgetron before joining this class or before considering joining this class, please press that button, raise your hand. So most of you, as far as I can tell, have not used Gadgetron before, and this is your first introduction. This is great, because I will tell you what you can do with it and what it is. Gadgetron is an open source streaming framework for online MRI data processing. So to break that up in parts, it's open source, meaning that it's free. You can go and download it, play with it. You can, if you want, you can compile it and sell it. There are really no restrictions on what you can do with it. It's a streaming framework, meaning that we process data as we receive it. This allows us to do real-time applications on the MRI scanner, and online. That means that it's on the scanner online. We're sending images back to the scanner during the scan, rather than collecting all the data, reconstructing offline at your computer later. You can use Gadgetron that way, but you can also use it at the scanner. It's a tool for doing rapid prototyping, both when you're prototyping new reconstruction techniques, but also for prototyping new sequences, because Gadgetron allows you to interact with your acquisitions to really see what you're getting from the scanner in a nice vendor neutral way. And finally, it's a toolbox for MRI construction. So everything in Gadgetron is built on top of these toolboxes. We have a toolbox for non-Cartesian Fourier transform for wavelets, for image registration, for a lot of low-level things like that. And then there are a number of toolboxes built on top of that for doing things like coil combination or doing a graph reconstruction. And a lot of people are just using the toolbox part and not the streaming part at all. So you can pretty much choose the part of Gadgetron you need, or all of it, depending on your specific application. It was started back in 2010, so we've just had our 10th birthday. It was started by Michael Hansen and Thomas Engel Sørensen, and I joined like half a year later. Since then, there's been more than 4,700 commits, and Gadgetron is about 120,000 lines of C++. And you can see this is like a plot timeline of the commits. You can see there's some very big commits in the beginning, and they've gotten a little smaller since then, mainly as things have stabilized, but it's still a very active project. The next question is, what is Gadgetron used for? And there are a lot of applications. I have not included all of them here, but we have a very active cardiac community. So we have applications like cine imaging, perfusion, real-time cardiac imaging, T1, T2 mapping, things like that. We have a very active neuro community doing functional imaging and qMRI. There are people who are doing PET MRI using Gadgetron. The SURF project are using Gadgetron as their engine for MRI reconstruction. There are people doing thermometry, DC imaging, and many other things. Gadgetron is also used clinically. So this is a map of clinical cardiac deployments supported by the NIH. So these are not all the clinical deployments, just the ones that are supported by the National Heart, Lung, and Blood Institute. So there are about more than 40 of these sites around the world, mainly in the US and in Europe. And the reason why you might want to use Gadgetron clinically is simply because there are applications in Gadgetron that let you do things that the vendor product doesn't. And I'll show you some of those during the talk today. But for now, we need to get a little technical and talk about what is a gadget. So Gadgetron has its name after the gadget, and it's sort of the key concept in Gadgetron. So a gadget is a unit for processing data, and it receives its input messages or input data through an input channel. So this gadget here just got 3 lines of pre-acquisition lines from the MRI. Then it processes the data. So it might have taken the 3 lines and put them into one K-space, one combined K-space. And then it sends data on to the next gadget via another channel. And you combine these gadgets by chaining them together, so one after the other, and they process their data asynchronously, meaning that like all the gadgets can be processing data at once. So if we look at an example here, we have the client, which could be an MRI scanner. It could be just the local client that's shipping with Gadgetron, just running on the same machine as Gadgetron itself. And it's sending acquisition lines to Gadgetron. They're going through the gadgets. Now the acquisition lines are coming, they're being processed, combined into a K-space buffer. They're being reconstructed. Then it's doing some post-processing and sent back to the client. And what's important to note here is that while the images are being reconstructed, the first gadgets are have already begun post-processing the next acquisition lines. So this allows us to do reconstruction with a very low latency and enable us to do things like real-time reconstruction. So to sum up, a gadget is an asynchronous unit of computation, to be a little technical. Now, let's have an intermezzo and talk about a very concrete application. So at the NIH, they developed a real-time spiral MRI for invasive procedures. So Adrian Campbell Washburn and colleagues, they developed a reconstruction in Gadgetron, allowing you to do to use the MRI for guidance during surgery. So here and to the left, you see 2 surgeons operating on a patient, and then they're performing a cardiac catheterization. And you can see on the wall here, that's a that's a live update of the reconstructed image, reconstructed with Gadgetron. They can do on-the-fly adjustments, so you can like change the position, orientation. They do some distortion correction. Then they do a GPU-based non-Cartesian reconstruction, and all this allows them a frame rate of about 10 images per second. So I think that's a really cool thing, and very much pushes Gadgetron to, well, shows you what Gadgetron can do. So if we look at what that chain looks like, so this is a slightly simplified view of what they're doing, but that chain would consist of something like a noise adjust gadget, which does noise pre-widening of the individual acquisitions. That moves on to a PCA gadget, which does coil compression. So you go from 16 coils and reduce down to just 8. And they're collected in a spiral prep gadget. What it does, it takes each acquisition line, attaches the correct spiral trajectory, and calculates the coil sensitivity maps, packages all that up in one buffer, and sends it to the next gadget, which performs the actual conjugate gradient sense reconstruction. Then that's sent on to the extract gadget, and all that does is essentially produce the magnitude image, which goes back to the scanner. Another real-time application is actually done at the University of Bordeaux, where they're doing ablation therapy, and they're using Gadgetron to do temperature mapping, thermometry, and they can use that to do motion tracking, to correct the treatment as it's happening, to verify that everything is working as intended. Okay, so let's talk about what a gadget can do. Like, it can do anything you want if you make it from scratch, but the gadgets that are already in Gadgetron when you download it. Now, the gadgets, they mainly operate on 3 different kinds of data. They either operate on acquisition lines, like individual lines of K-space, or on a K-space buffer, so like a complete K-space, or on images. And for acquisitions, we have things like the noise adjuster I already talked about, coil reduction, EPI correction, and this gadget here called accumulate and trigger. And essentially what it does is it takes acquisition lines and bundles them together in a K-space based on some triggering parameter that that the user defines. For the K-space buffers, well, the gadgets that accept these as input, they are mainly the ones doing actual reconstruction. So we have Cartesian reconstruction, where grappa is definitely the workhorse of Gadgetron. We have a very robust grappa implementation that's being used as the baseline in a lot of different applications. We also have Spirit reconstruction with and without compressed sensing, and we have a Cine reconstruction where they're doing a K-space binning, and they're doing motion correction. In the non-Cartesian side of things, we have a bit more variety, simply because non-Cartesian applications tend to be a little less one size fits all. And we have like just standard gridding, CG sense, compressed sensing sense, but also things like spiral chemical shift imaging and off resonance corrected gridding. For the images, so after the reconstruction, we have things like the T1 and T2 mapping that accept a number of images and then perform the fit of these functions. We have a fat water gadget that performs the B0 mapping and then extracts fat and water images. We have gadgets for doing Bayesian denoising, Maxwell correction, and many other things. Now let's go on to the second intermezzo and talk about another application. So we at the NIH, he developed an algorithm for doing free breathing cardiac cine. So this is an L1 spirit recon. So compressed sensing spirit with motion correction. And essentially what you do in this application, you take a number of slices, acquire a number of slices throughout the heart, and you want to get these cine images without the breathing motion. And if you're not familiar with cine imaging, sort of the standard way of doing it is with a breath hold. But when you have children, for instance, that can be very difficult or impossible to do. So the acquisition time is only 8 seconds per slice. That's not too bad. But the reconstruction time is about a minute per slice, and we'll get back to that in a moment. If you look here, so this is these are images from a 5-day-old infant, and you can see you have quite nice motion-free cine images. Next to it, we have some images from an older child. You can see they're a little more detailed, simply because an older child is bigger. But so this is a really killer application. A lot of hospitals were very interested in deploying this, but the reconstruction time was a barrier. So the acquisitions, they don't take that long, but waiting another 10-15 minutes for everything to finish, that was a showstopper in many cases. And that leads us on to the next topic, which is distributed Gadgetron. So Gadgetron can distribute a reconstruction. So you have the main Gadgetron here that's receiving data from the client, and then they're going through the initial gadgets. But then they reach this distributed node, which sends the data out to a number of other Gadgetron instances on a cluster. They process the data individually and send it back. The main Gadgetron does the post-processing, sends it back to the client. So Hui actually, he developed the initial implementation of this, and we've been reworking it a little bit to make it easier to use for many other applications. So the cluster itself, like it could be a local cluster if your university or hospital has one of those. It could be in the cloud, so that's actually the main, the typical way it's being deployed clinically. But it could also just be like gather up all the laptops in your office and start Gadgetron on them. It doesn't really have to be all that fancy if you have an application that needs the extra computational power. So when we did all this, the result was that acquisition and reconstruction could be done in under under 6 minutes. That's actually less than a typical breath hold would have been. And it's about a 30-second delay for the images to start arriving back at the scanner after the acquisitions have finished. So yeah, this is deployed at quite a few sensors around the world. Finally, I'd like to talk about the external language interface in Gadgetron, and you'll be meeting that a lot during the online class. Gadgetron interfaces with Python and MATLAB could be extended for other languages, but those are the ones we support currently. And that allows you to do interactive debugging. So this is Python and MATLAB without any restrictions whatsoever. Like you can have Gadgetron inside your MATLAB instance and use it interactively like you would with any other data, or you could use it in your IPython notebook. This is really MATLAB and Python without any restrictions, and we improved the support for this quite a lot in Gadgetron 4.1. For instance, if you tried to use Gadgetron and MATLAB previously in Gadgetron 3, well, I mean, it worked, but every new release of MATLAB would mean that things were breaking. We typically only supported a single version of MATLAB because things were sort of very fragile. Now you just install the Gadgetron MATLAB package in MATLAB and it just works. So a lot of people have been using this. For instance, the people at CNRS, they had a reconstruction developed in MATLAB and BART for doing MP2RAGE compressed sensing. They want to do T1 mapping of the brain, and with the MATLAB gadget, they could just put that into Gadgetron, put it on the scanner, and what you see here is actually the T1 map on the Siemens console. Another application that we've been developing is for denoising using AI. So we trained a neural network for denoising cardiac images, and this is another example from Hui, where he's applying that on a brain scan, and hopefully even through Zoom, you're able to tell that the image on the right is looking much nicer than the noisy image on the left. Another application that's been developed using Python in Gadgetron is Hui again developed an auto segmentation algorithm to detect the left ventricle on the heart on perfusion when doing perfusion mapping and doing automatic analysis of this perfusion image. So you end up with an automatically generated report back on the scanner that delivers the quantitative parameters that the physician needs. And finally, Valerie, who just heard speak, he's been developing an application where he's using all of this. So he has a chain that starts out with a couple of C++ gadgets for doing the pre-processing. Then he's using a MATLAB gadget with BART for doing the image reconstruction, followed by a Python gadget for doing AI-based segmentation, and at the end, it goes back to C++ for image post-processing. And it allows them to visualize the segmented heart directly in their software. So that was all from me. Thank you very much. If you have any questions, you can ask them, I guess, either now or at the end of the day. You're also welcome to email me. And in Slack, there is a questionnaire that we would very much like all of you to take, so we know a little more about who you are and who are interested in Gadgetron. Thank you.